So in this video, I'd like to go about showing how we use the user-defined function block in the Micro800 and in the CCW, or Connected Components Workbench software. So a user-defined function block is basically a piece of code that I can create once and reuse it multiple times. And it's kind of a parameterized function block or subroutine where I can basically send in the inputs. It'll solve some logic, and then I can pass the outputs out. And I can basically reuse that code over and over again. To do this, I've got a project already created. I'm going to use the Micro850 simulator because it's going to be a little bit easier to show what I want to do here. So I'm going to go ahead and open up the simulator. I come to Tools, and I say Micro800 Simulator. So right now the IP address is defaulted to the loopback interface. I'm going to leave it at that. I'm going to go ahead and start the simulator just to get it going. Note that I am using the developer edition, which basically the simulator will run for 1 day. If you're using the free standard version, you can still use the simulator. It only runs for, I think, maybe 10 minutes at a time, which is sufficient amount of time to do some testing. So I'm going to go ahead and, so I have it running. We can see that it's powered and running, and the green is on there too. So I'm going to go ahead and minimize that for a few moments. So where I kind of came up with this concept is recently I was kind of going back and looking at some of the basics of microprocessors and digital logic, and was kind of looking at, half adders and full adders, and basically, adding binary numbers together and then doing it with logic gates. So this actually makes for a really interesting example just to show the capability of what a user-defined function block can do. Now, would you actually need to do this in the Micro800? I don't think so, but it's just a good exercise. So the concept here is that if you were going to build a half adder or a full adder out of either logic gates or even out of relays themselves, electromechanical relays, you would create this half adder and full adder circuit. So if we're going to add two binary numbers together, like we have input 1, input 2, or A and B, I'm going to keep it simple with a 4-bit number, just to make it a little bit easier when I go and build the code. But if we're going to add two binary numbers together, we know if input A is a 1 and input B is a 1, well, 1 plus 1 in binary actually becomes a 0, and we carry the 1 over into the next position. So this is a decimal value of 1, and this is a decimal value of 1. Well, 1 plus 1, of course, is 2, but in binary, 2 is basically a 1 in the second position here. Okay, so to do that, and kind of gone down a little bit of the YouTube and internet rabbit hole, and was researching half adders and full adders a little bit, and to do it in logic gates, basically to make a full adder, we need to basically combine two half adders. Okay. So again, I'm not really trying to teach digital logic here, but just kind of showing you what I'm going to set up. So for a half adder, basically our inputs A and B will go into an exclusive OR gate, and they will also go into an AND gate. And then we get the sum out of the exclusive OR, and then we get the carry out of the AND gate. So that carry is basically what happens here, right? We're carrying the 1 over to the next position. And then to make a full adder, we need to basically combine two half adders, and then these carry outputs go into an OR gate to determine if we have a carry out to the next position. And then next, and the reason why this is a good example for a user-defined function block, is we can basically string these full adders together to make what's called a ripple carry binary adder. So basically each one of these full adders kind of, basically the output of the first full adder kind of gets sent to the second full adder, to the third, and to the fourth, and the fifth, and so on and so on and so on. So to make it simple again, I said I'm going to do a 4-bit number. So that will basically be 4 full adders kind of cascaded together, or in this, well, again, terminology, ripple carry. We can keep doing this, 8-bit, 16-bit, whatever we want, right? So we're going to build this, basically build this into a user-defined function block, and then I can reuse that in the code. So let's come back to our logic. I don't have any programs here. I'm going to go ahead and create a user-defined function block first. And when I say, I can right-click on it, say add, we can create either a structured text ladder diagram or a function block diagram block. I'm going to go ahead with function block diagram. I'm going to go ahead and rename it to adder. And I'm going to double click. And that opens up our function block space. So I'm going to go ahead and add the actual instructions themselves. So right click, show instructions, and if you remember from a moment ago, our very first gate is a exclusive OR gate. So it just so happens that we have logical functions in the Micro800. So again, that's partly why I just thought this was an interesting exercise. So there's our exclusive OR gate, inputs 1, 2, and the output. I'm going to go ahead and add a second instruction block, and this will be an AND gate. And I'm going to go ahead and add a couple of variables here. All right, we need to have our input 1 and input 2, and we also need to have what's going to be called our carry in. So that's kind of our inputs at the moment. And I'm going to go ahead and copy and paste this to make it a little bit easier. And then if you remember back from the drawing here, we had an exclusive OR and an AND, and then a second exclusive OR and AND. So that's the second half adder. And then I also had to have an OR gate down here for the carry out. So if I come back, I'm going to go ahead and add one more instruction down here. I'm going to call it, make it an OR gate. All right. And then, of course, we're going to need two more variables at this point. We're going to need an output, and we're going to need this carry out. All right. So the carry out actually connected there, so that's fine. The sum, basically the output of the second exclusive OR gate will go to the output, or the sum. So the input will go to the first exclusive OR, and then we will also combine the input to the AND gate. All right, so going back to our diagram here, A goes into the exclusive OR, and it gets paralleled into the AND gate. And then the output from this first half adder goes into the second half adder, and then the carry in goes into the second. So basically, the output goes into A, and this carry in goes into B of the second half adder. So I come back to my diagram. This will connect to there, and this will connect to there. And then I will also connect the output to this AND gate and to there. Now the lines kind of get written over here a little bit, and we can always clean this up later, but for points of this. And then basically they only got two more connections to make here, and that is the outputs of each AND gate will go into this OR gate to determine if there's a carry out. All right, so that's basically half adder 1, half adder 2, and then the OR gate. So I can now, basically, this is now my full adder block that I can reuse multiple times. Now the only other thing I'll do next is define the variables. So these will be local variables. All right, so we have global variables, which are of course accessible by all programs. Local variables are only accessible to this local program, what we're calling adder. So I'm going to double click on local variables, Eventually it opens up. So I'm going to need to create several variables here. So again, I have an input A, input B, I have a carry input, I have the sum output, and the carry output, essentially. So, so the key is that when we create these variables, we'll call it input A, and it needs to be a Boolean, and the direction is we want to make this a variable at an input. All right, so this will basically be an input into this function block. I'm going to create a second one called input B. It's also a Boolean. It's also a variable input. I have one more carry, one more input. I'm going to call this one carry in. And again, this is an input. And then we're going to have two outputs from this function block. One is the sum. So we're going to define this as a variable output. And then the other one is carry out, also an output. Now, note that there's also just a var or variable. So if I needed to, I could create variables that are only kind of used internal to this block. They're not going to be something that gets passed in, or not a variable that gets passed out, just gets used internal to the logic. In this situation, I actually don't have any internal variables to reference, so I'm not creating any of that type. So I come back to my adder now. Now it's a matter of populating those variables here into the right spots. So for my for this one, be input A. So I'm going to make sure I'm picking from the adder. There's input A. We're going to choose input B for this one, and we're going to choose the carry in for that variable. For my two outputs, I'm choosing the sum, and then for this OR gate, it's the carry out. And that's it. I'm going to save it. That's all I got to do. So now I'm going to come back to my main program. I need to first create one. So I'm going to go ahead and add a program. And I'm going to go ahead and make this a function block diagram as well for the main program, because it's going to be a lot easier to draw and show that ripple carry here. So I'm going to go ahead and double click on program 1. And here again is program 1. So again, this is a user-defined function block. This is the main program. This is what's actually going to execute. This does not automatically execute when the controller goes in the run mode. This program 1 is what executes. So to basically build the ripple carry, I'm going to basically do this, where I'm going to take 4 of these full adders that I just created, and I'm going to basically give it an input and then tie the carry out to the carry in of each full adder. So to do this, I'm going to come back to the toolbox. I'm going to say instruction block. Now what's kind of nice about having created this user-defined function block is now when I say show instruction block selector, I type in adder, and there is my user-defined block. And there's my input A, my input B, my carry in, my sum, and my carry out. Right? So now I can copy and paste. I'm going to paste it again and paste it one more time. So basically 1, 2, 3, 4. That is basically mimicking 1, 2, 3, 4. So in this case, we're going to carry, again, the carry out will feed the carry into the next block. So we can string these along just like this. And then each of these adders will have a separate input for each A and B and a separate sum out. So that brings us back to our variables again. We're going to have 2 variables. And we're going to have one variable to come out. Now, to make life a little bit easier, I'm just going to change the color of a couple of these. So we can kind of change the color and help them kind of stand out a little bit better. So this will be our input 1, or A. This will be our input B. And what we'll do here is, being that I am using the simulator, and I said I'm going to use a 4-bit adder, I'm going to use these first 4 inputs as my input 1. So binary, that's going to be my my 2 to the 0 position, 2 to the 1, 2 to the 3, and 2 to the 4. And then I'll use 7, 6, 5, and 4 for my for this input B. And I'm going to use 3, 2, 1, and 0 for my output. So basically we can represent the binary number and then see the binaries get added on the outputs down here. So I'm going to go ahead and use 3 for input for the first adder, 2 for the second adder, 1, and then 0, just to kind of make it look like a binary number here, basically. So what we'll do is, just to kind of help make this go a little quicker, I'm going to define this first one and then do copy paste. So we're going to do, again, DI3 for the first input, and we'll use DI7 for the input B. I'm going to go ahead and do a copy paste, and we'll drop them on the next adder. Paste again on the next adder. Paste again on the next adder. So now, being that I've done this, it should make it go a bit quicker. I'm going to make that 2, make this 6, make this 1, make this 5, and make this one 0, and make this one 4. Of course, we have to draw our lines and connect to each input for each adder. And we do the same thing here with the output. In this case, we're going to tie it to the actual output. So that'd be DO. And I'm going to use, again, 0, 1, 2, and 3. But I'm going to go with 3 here first. Copy, paste. Paste. And paste. So we will change this one to 2. This one to 1. And this one to 0. And last thing is connect the dots. All right, so I basically, again, just built my ripple carry adder based on making a full adder function, user-defined function block. So I could reuse this code over and over and over again. And basically, we're just going to pass in different inputs into each of these adders and then get a different output for each adder. So basically, that's it. So once again, I have my simulator powered. The IP address is tied to the loopback. So when I come back to CCW, if I come to my Micro850, I'm going to say connect. I'm going to come to the AB ETH-1. We see right here that the 127001 is the Micro850 simulator. I hit OK. It says, do you want to download? So right now it is actually connecting to my emulator controller. It's downloading the program. You notice how it just went into the program mode right there. And it says, okay, download complete. Do you want to change it back to remote run? And we say yes. And there it went back in the run mode. So the point of all this, again, was to basically build a, this little logic that will add these two binary numbers. So again, we have input A, input B. So when I put in a 1 and a 1, I'm going to get a 0, 0, 1, 0 as the sum. So we're going to see that right now with these lights. So just to show the basics, if I don't even have the input B turned on, if I turn on input A, okay, so I turn on the first output, second output, third bit, fourth bit, right? So remember, think of this as a binary number where this is the least significant, this is the most significant. Now if I do the same thing for the second, okay, turned on the first one, turns on the second one, oops, sorry about that, turns on the third one, and turns on the fourth one. So we know that, basically that would have been 0, 0, 0, 0 plus 0, 0, 0, 1, and that basically turned that light on. Now, if I turn on basically 0, 0, 0, 1, and then 0, 0, 0, 1, look what happened. It actually added it. So it took the, it now, so this is, again, this is 2 to the 0, this is 2 to the 1, so this would have been the 1's place, essentially. This is now 2. So, again, decimal 1 plus decimal 1 equals decimal 2. Binary 0001 plus binary 0001 equals 0010. So the adder worked. And if we come back here into the logic, we see that, true, true, and then we can see that this output is false, but we have a carry as true, and the carry got passed into the next adder, and we see that even though these two inputs are false, since the carry comes into the second adder, then the output is true. So again, why would you need to build a ripple carry binary adder in the Micro800? I don't think there would ever be a reason to do so. If anybody knows, please feel free to comment. But the exercise was really to show you how I was able to build, one piece of logic and reuse it over and over again, and even cascade them together, just to do that. So really, again, the key is the idea of being able to use reusable code with user-defined function block. And again, we can create a user-defined function block that is either based with structured text, ladder diagram, or function block. So we have the ability to create user-defined function blocks in any of the languages that we choose, and then we can use that function block in any of the languages that we choose up here in the main program. I just happened to use function block, and this was function block, but I could have easily have made this into a ladder, or I could have made this in the ladder and use up here in function block. So a lot of versatility in the ability to reuse your code.